And we're still going. So let's get this. We were in the middle of number 4. I said that we're looking for if we have the samples, we're trying to determine which site these came from. So we looked at the first one. We know that all 3 should add to about 20.5. We eliminated site 1 because with a typical value around 7 and 13, that would add to way more. So if we look at the middle one, 6, 7, and 3, this seems like a 6, 7, and 3. This would be expected to be a little bit lower than 20.5. And here we're looking at a typical value of 6, 7, and 7. That one's close to 20 at that point. So I'm guessing that this one probably came from site 3 if we're looking at the typical values. Would add to around 20 and actually look at that as 6 plus 7 plus 7 again. And, maybe a chemical Y is just a little bit, median's just a little bit higher than Z. So maybe we can get that as maybe 20.5 if we justify that Y is 7.5 instead of 7. So on to B part 2, suppose only one chemical could be analyzed in the piece of pottery. Which chemical, X, Y, or Z, would be the most useful in identifying the site? So looking up here again, which one's going to be the most useful? Well, if you look at all of the X's, so we're going to be looking at which chemical is really, really different. If I'm looking at all the X's, most of the X's are pretty much the same with typical values at 6 or maybe about 7. They're not very spread out. If I'm looking at chemical Y, Y is very high on site 1, very low on site 2, and right in the middle on site 3, which is good. So those are drastically different. We might be able to identify them. Contrary, that last one, just look at it anyways. On site 1, chemical Z maybe has a typical value around 7, and same around 7, and on site 3 also around 7. So these are definitely a little bit spread out, but most of the data is still really kind of close together. The one that's drastically different would be chemical Y. I believe it's going to say justify your choice because it's percent of total weight is drastically different from site to site. All right, so number 5. The table and the bar chart summarize the age at diagnosis in years for a random sample of 207 men and women currently being treated for schizophrenia. Does the data provide convincing statistical evidence of an association? So what type of test is it really asking us? Are these percents or Z's? No. Are these means or T's? No. All of these are counts. We should be thinking about running a chi-squared test, probably for independence since it's asking association. So if we have the actual observed values, we're going to have to do some conditions, and we're going to have to find some expected values. So let's start with conditions really quick. Data is random. It says so. Random and independent in counts. And even though there's one cell that has less than 5, once we do the expected values, I'm pretty sure it's going to be over 5. So we could say, and at least 5 are expected in each cell. You'll also have to say the 10% rule. So this sample is less than 10% of people with schizophrenia. I'm going to abbreviate that SCHIZ, schizophrenia. So take a second. What you should do, let's look at, since women and men are not a 50-50 split, 119 over 207 is about 57.5. That leaves the men to be 42.5. So take these and find the expected values. So you'd be finding 57% of 15, 57% of 30, 57% of 63, write it here. 57% of the 99, write it here. Likewise, then you're going to find the 42.5% of 15, write it here. 42.5% of 30, write it here. Blah, blah, blah. You get the idea, get the idea. And surprise, there's your expected values. So when you did 57.5 times the 15, you should have gotten 8.625, or the 57.5 times the 30, you should have gotten 1725, and so forth. And then the 42.5 times the 63, you should have expected 26, almost 27 men, 30 to 39, to be diagnosed with schizophrenia. Put both of these in the calculator. You should have two lists of observed and expected. And then make sure that they align. So cell 1 with cell 1, cell 2 with cell 2. In that, make sure that they line up perfectly because they are corresponding. And you should run a test. Chi-squared should come out to be 10, almost 11, with a p-value of 0.12. It never hurts to draw a graph. Remember, chi-squared is always very heavily skewed right. That p-value is really small, so you might want to shade it and identify that we have a very small p-value. I wouldn't even say 1% is very small, but 1% is significant. So we have a small p-value. So we can reject the null hypothesis with alpha, let's say it's 0.5. Now, if you made alpha 0.1, you'd be failing to reject. AP wants you to be able to say why you made that rejection. So say that alpha's at 5, because you can reject that at 5, but with this being over 1, if you made alpha 0.1, you have to be saying you're failing to reject. And I'm just realizing now, actually, we didn't write a null hypothesis yet. Whoops. Null hypothesis is there is no association between gender and age of diagnosis. This really should have been done before we did the expected values. And then the alternate hypothesis is there is an association. I'm going to run out of time in just a second, so I'm just going to verbally say it. We have a small p-value, which was right above 1%, so we reject the null hypothesis at alpha 0.05. You should also write that there is an association between gender and age of diagnosis for schizophrenia.